Modeling a string loose at one end and tied at the other. Now, this is not the most practical, useful form as far as a string goes, but this actually models other things very, very well. What I'm going to do right now actually models this extraordinarily well. The tube is open at one end and closed at the other where the water is. So if I have a string that's tied at one end, so it looks something like this, and loose at the other, say I got a nice ring and a real nice frictionless pull, that end can swing up and down. If I start shaking this thing, the first resonance pattern I'm going to see is going to look something like this. It's the very first resonance. And okay, the very next resonance, well, just like before, I just keep adding a node. So the next resonance is going to look something like this. Once again, I'm exaggerating drastically just so it's easy to see. And the very next resonance, will look something like this. There's the loose end right there. So now I have to be careful. If it was me and if I was in charge, I would say this is my n equals 1 resonance, and this is my n equals 2, because it's the second resonance. And I would say this is my n equals 3 resonance. It's not done that way. So let me take a step back and look at this thing. I go, well, how far is it from here to here? Because before we did it, we wrote the length of the string in terms of a wavelength somehow. And I say, well, if I look at my wave pattern, I know that from a node to node is a half a wave. So if I looked at something like this, from here to here is half a wave. From a node to an antinode has got to be how far? It's half that again, so it's a quarter wave. So the distance from a node to an antinode right here, that's going to be quarter wave. So L is equal to, I got a nice quarter wave like that. And then I look at the very next one. I look at the very next one and I go, well, now I'm just adding in another half wavelength. So now the length of the string is going to be, I got a quarter wave out in front still, and I got a half a wave sitting on after it. And then if I go to the very next one, I say I still got this quarter wave out front, but then a half wave and a half wave. So you have the length is equal to, I get that quarter wave hanging out in front, and now I have 2 half waves. And I could kind of infer from that I'm seeing a pattern. Each time I get to the next resonance, I'm adding on a half wave. So the length of the string in general is going to be equal to, I'm going to have a quarter wave out front if it's loose at one end, plus an integer number. I'm going to use an n again, which is bad, but I'll do that. Like that. And then I'm going to use the same thing we did before. We said, you know, this has to be a traveling wave. So I know that the frequency times wavelength has got to be equal to velocity. So I can say the frequency times the wavelength is equal to velocity, so I know the wavelength is v over f. So I could write this as the length of the tube is equal to, this is going to be v over 4f, plus this is going to be n v over 2f, like that. And once again, you'd say, oh, we want to write it in terms of frequency, so I'm going to multiply both sides by f, divide both sides by L, and I get the resonance frequencies are going to be V over 4L plus NV over 2L. And when I first started teaching this stuff, I always left it like that. It always made sense to me to leave it like that. It always worked out. But I've kind of changed, and the reason I've changed is historically you don't talk about a tied loose string, or more importantly, a sound tube that's open at one end and closed at the other, which is what this is modeling. You don't talk about it this way. What they will say, and I really think this goes back to music theory from the 1500s, that you only get the odd harmonics for something like this. And the way they explain that is they say you can factor this. You can write the resonance frequencies are 2n plus 1 times v over 4L. Okay? And then they'll say, well, 2n plus 1, n's just an integer, so 2 times something plus 1 has to be an odd integer, right? So instead, they'll write it like this. They'll say the resonance frequencies are going to be m times v over 4L, where M is going to be 1, 3, 5, 7, 9, like that. And they will say, you have to be very careful of this, and I'll try to be very clear if it comes up. You have to be very careful that when you talk about a tube, like a tube that's closed at one end and open the other, you only get the odd harmonics. You can't talk about second harmonics. It makes no sense to me at all. I think if this is the first resonance, this is the second one, this is the third one, this is the fourth one, this is the fifth one. But they'll always talk about this in terms of, oh, you only get the odd harmonics. And we used to book one time that really, really harped on that, and I don't know that it's that. I mean, whatever. That's what they mean when they say you've got. Let me put this on top. If I have a tied, loose string, my resonance frequencies, the M and this isn't multiplying it by M, they'll very commonly put a little subscript down here to stand for the mth resonance is going to be M times V over 4L, where M is going to be 1, 3, 5, 7, like that. You only get the odd harmonics. Once again, where it's interesting is that when we do, the nice thing about looking at strings, if you look at strings and understand the strings, the sound stuff is almost exactly the same. And before I do any of that, I want to do a couple demos with sound, just to kind of hear it. And you guys probably heard this between like 8 different noises in the lab.